Good afternoon. I'm your neighbor here in Santa Clara. Work for Ericsson, and we basically move bits over thin air. So we've been doing this for 140 years, more or less. So several people this morning mentioned 5G. I'm trying to demystify it for you a little bit. So just a few words about my group. We're Ericsson Research. We're the corporate research organization of Ericsson. We're headquartered in Stockholm, Sweden, and we have several research areas. Mine is the radio area, which is kind of corresponds to the big business of Ericsson, along with the network area. But we also have other research areas that correspond to business units or to new things that we're looking into. We have sites all over the world. Our latest site is in Turkey. But let's move on to the topic here. So just a couple of minutes on the basics, since I assume you're from the other side of the house. Just very high-level abstraction. What do we do for a living? We try to maximize capacity subject to some sort of user quality criteria. So we try to jam as many bits per second, per hertz, per area, per whatever, as long as the customers are happy, right? That's what we do. What is the scarce resource here? By far, it's spectrum. You're not making any more spectrum. Everybody's fighting over spectrum. If there's spectrum, we want it, right? Everything else we can add at a cost, and I will give you a few examples of that. The most effective way to make your system better is antennas, whether they're bunched together in an array or distributed or small cells or big cells or whatever. Of course, the air interface itself, like 5G and 4G and so on, which is influenced by information theory and coding theory and communication systems and so on. We do all kinds of signal processing, classical signal processing. Now there's increasing kind of machine learning type processing, but it's all from the same side. You can add power, you can always blast more, but in a mobile network, it's only useful to a point, because then you start screaming over each other and nothing happens. So power is not as big of a deal as the other things. Okay, so what do we do with antennas? The original cell, think of it as like this big circle. And the first thing you can do is sectorize it. The world is covered with Ericsson three cell sites, as they call them. So you can point like 120-degree beams in each direction. That, of course, helps a lot in terms of increasing capacity. The next thing you can do is so-called densify. You just make the cells smaller and closer to one another, and reuse the same frequency over and over and over. That's what we do in cities, say, right? If you're in Manhattan, there's a cell at every street corner and every intersection and so on. Then, if you know where people are, and people are very unevenly distributed, of course, if you know where they are, like at an entrance to a building or an airport or a train station or something like that, you can put a small cell right there, and that's extremely efficient, right? Because the distribution of people versus geography, if you will, is extremely uneven. So if you just cover the whole place, it's good for getting a signal. But if you want really efficient network and you knew where people are, then of course you can put the cells there. Then you get into the fancy stuff. In 5G, we do a lot of this active beamforming where we follow the user, right? Which implies that you know where the user is, at least from a signal perspective. You don't need to know really where they are. So this is kind of, if you're familiar with synthetic aperture radar, where they follow the plane without actually mechanically moving anything, that's kind of the same thing. You can connect the user to multiple base stations. That makes the system more robust. You can serve multiple users at the same time from the same base station, like they call it multi-user MIMO or something like that. And you can follow them at the same time. And of course, you can do all of them at the same time, and it gets more and more complicated. This is very much what we're doing in 5G. Now, the actual overview, I like this picture because I think that I started working here 10 years ago on, let's say, 2009 or 2010 or whatever you want to think of it. And then we hack away at it in research, then we get system engineering in, then they build a test bed, then we start talking to our competitors and friends and to try to make all the components start to kind of hang together. There's this big research project like the EU project that sort of help out along the way. Of course, there's also projects in the US and China and other places. Eventually, things start to look similar enough that you can go to standardization. We're a very standards-oriented industry. So we go to this industry body called 3GPP, and starting in so-called release 15, we start doing the so-called 5G, even though I don't think there's any document that's called 5G, but it is 5G. We call it NR for new radio. And now we're finishing up release 16, which has even more features. And release 17 starts in a few weeks, and so on. So there's a rhythm to this whole business. But we start very, very early, especially on the RF stuff. It takes a very long time to get these things from, the lab into something that you can deploy in millions of units all over the world and so on. Okay, so what is it about? You can think of the little corner here. Mobile broadband is what essentially 4G was about, smartphones and tablets and all that stuff. So that will continue and expand and get bigger and so on. That is kind of like the momentum from 4G will carry into 5G. Then an easy one, in a way, is fixed wireless access. The bit rates are high enough to compete with home service. And in a way, it's easy because the endpoints are fixed. So a lot of the hyper complexity of following people around is not there. So the US operators have been deploying fixed wireless access, and they have these units that you can put next to the window or on the wall and so on. And then you get into kind of strikingly different things. Massive IoT is where you're trying to serve many, many, many little sensors and actuators and so on. So the problem here is not high bit rate, but being able to handle them all at the same time in a way that they consume very little power. They can wake up only a few seconds a day, or whatever the problem is. So that's one corner. There's another corner which is critical IoT. This is where you have machines that are expensive and you're connecting them and you're not worried about battery, but you're worried about extreme reliability. So, industry, factories, large vehicles, etc. So this is kind of in a very big picture where we think it's going. Some key numbers, I won't read all through of them. So the first thing that, of course, people notice is the sort of the experience data rate. This is what a consumer using some device will feel is the rate coming at them, and that's really what matters. Latency, at least over the mobile network, is going down significantly. Of course, you still have the other latency, which is going to the server and coming back, which is not under our control. But, of course, as many of the people this morning mentioned, you can bring the computation to the edge, and then from the edge to the device is not a long distance, and of course that's how it works really well. You can connect many more devices, you can improve the availability, the reliability, the energy efficiency, the security, you name it. Of course you can't do them all at the same time for everybody, but you can reach the corners depending on the application. Okay, this is the world that I live in, the 3GPP standardization. So as I mentioned, we're kind of now, of course, we're at the end of 2019. We're finishing up release 15. People are fighting the last few fights over release 16 and so on. And then they will start so-called release 17, which is further enhancements to both to new radio, NR, which is 5G, and LTE, which will be around for a very long time. But LTE improvements will kind of slow down very quickly. So it will become a stable standard with very few changes. So maybe release 17 will be the last one which will have LTE components, or maybe not. But at the same time, there's on the top part, there's the ITU, which is the UN equivalent for communication. And it's not very important for the US, but for other countries, it's extremely important that you say, okay, whatever we're deploying here and spending half of our national budget on is actually some kind of international standard that's been called 5G by this body here. So 3GPP will submit a document and a whole bunch of tests and so on, saying, look, we satisfy what you wanted to call IMT 2020, and these guys will say yes, no, whatever. Some other body having nothing to do with 3GPP could do the same as well, right? But so this whole machinery is ongoing. This is how the telecom industry functions. Okay. Those are many technology components that are going into 5G. As you can imagine, it's a very highly complex system, and you get these technology components that start off in research in academia or in labs like mine, and slowly mature their way until finally some of them make it into the actual products. So I think I have a slide on the beamforming, but other things is if you are familiar with LTE, it uses something called OFDM, which is a way of dividing time and frequency resources, and 5G uses the same thing. There's something in the way we organize the information that makes it easier to improve energy efficiency, so-called ultra-lean design, so you can kind of lower the power of the transmitter and up it as needed, and many more components. And all these things come together, and some of them actually make it into the standard, and some of them die along the way, but this is what we're working on. The so-called MIMO. MIMO stands for multi-input, multi-output, meaning you have many transmit antennas and many receive antennas all working at the same time. Unlike, say, 4G, LTE, 5G has MIMO baked in from the start. So all the devices are multi-antennas and all the base stations are multi-antennas. And as I tried to convince you before, this is the most straightforward way of having very high capacity and bit rates and so on. And these MIMO schemes are good for any frequency ranges. So at lower frequency, you can use them to serve many people at the same time. At higher frequency, where the path loss is more of a challenge, meaning like the signal dies out very quickly. Then we use them to do beam forming, nice sharp beams that point to the user. And we can have hundreds of antenna elements in a tiny little array. Well, that's extremely useful. So this is what people think of 5G from a technical perspective is mostly the antenna schemes. There's something else which has the unfortunate name of numerology, which refers to being able to use the same structure in any frequency range. So most of the mobile networks, including 4G, were kind of below 2 gigahertz. They were all bunched in the lower frequencies. With 5G, in the US, we're starting at 28 gigahertz and 39 gigahertz, and now we're interested in 6 gigahertz and so on. So many different frequency ranges, quite far apart. But in order to make the technology be basically the same, we have these knobs that we can turn so that it adapts nicely. So this is what this is about. So as a result, you can have the same baseband, which is kind of the computer part of the base station, be the same whether you're using it at 28 gigahertz or at 1 gigahertz. And that's very helpful. Back to spectrum. There are many discussions ongoing. There was, I think, a meeting last week, I believe, or the week before in Egypt for the ITU, where they were fighting about which frequency ranges will be used in 5G. It's mostly these three here, the so-called low band, mid band, and high band. The picture there, if you go to the FCC website, you can create your own map that shows like each little frequency band who's using it now. And the idea is to show you that it's extremely busy. So there's no open spectrum waiting to be used anymore. If you want to grab spectrum, somebody has it, and there's going to be a fight of some sort. But in the US, the FCC has been very active. It's kind of leading the world in freeing up spectrum for mobile and other uses as well. So there was a 24 gigahertz 24 gigahertz band auction in the spring, and they're talking about other frequencies as well. There's a discussion going on now about the so-called 6 gigahertz band, which is above where the unlicensed band where Wi-Fi operates now. So now the Wi-Fi industry and the mobile industry are, staring at each other, and maybe they'll just give them each half or something. I don't know. This is an example of the kind of studies we do. I think this is the city of London, if I'm not, yes. And this is a very Ericsson kind of design. We take the different frequency ranges, we lump them all together in one single resource pool, and we try to assign each user to whatever frequency they are, is best for them at this instant. So this is an example of an outdoor deployment. And in this case, it shows that 75% of the outdoor users get over 1 gigabit per second, which is more than what they need today. And also the indoor users also are getting, some of them are getting above 1 gigabit per second. One of the issues with the high frequencies is that they don't penetrate very well through obstacles like, walls and windows that have metallized stuff in them. So this will be one of the things we have to deal with, is either have many more indoor deployments or figure out how to handle outdoor to indoor coverage. But this is an example of the kind of studies that we do. Another thing that Ericsson has been pushing very hard is this notion of spectrum sharing between LTE and NR. So today, when you start deploying NR, 5G, there's very few users that have phones or devices that can do 5G. But you want to get them started anyway. So instead of having one constant allocation, you kind of plug them in between the LTE users on the same frequency. So that allows you to kind of smoothly get up with the percentage of users that switch to NR. And eventually, it may become a fully NR band or a mix of NR and LTE. So this is the standard has the hooks for this, and then we have proprietary stuff on top of it to make it work our way. So a lot of the way that the vendors compete is they kind of mix the standard stuff, which they all know, right? It's public, with their own secret sauce that they add on top. And one of the things that allows is we have all of our customers who already have Ericsson equipment that does LTE. They can switch to this without changing anything. So at the beginning, they don't have to have this enormous outlay of cash just to serve the first 5G user. Anyway, so this is happening now. A glimpse about the deployments. As of October, I believe, we have 22 live deployments. Live means they're real. It's not like we showed somebody something. So Ericsson is an extremely conservative company. So they have the 75 commercial agreements mean, they signed and they did test beds and all the early stuff. Live means live. It's actually deployed commercially. The 4 US operators are very aggressively deploying 5G. Of course, you expect Verizon and AT&T, which feel that they are kind of leading the world in this stuff, to be pushing very hard, but also Sprint and T-Mobile, which are planning to merge, are deploying 5G. In particular, there's a band, the 2.5 gigahertz band, which the Sprint has, which used to be like the Bermuda Triangle of spectrum. Anybody who touched it, you never heard of them again. But now it is the prime real estate for 5G. So all of them are deploying. Korea is deploying very aggressively. Japan is deploying very aggressively. China will start now deploying commercially. The European circles are kind of misleading a little bit. Because of course, there are many countries and they're all starting to deploy, but Europe has been kind of slow on deploying new technology. They were way ahead in 3G, and it kind of became, a tight race in 4G, and now they're kind of behind. So our CEO, who is Swedish, is always flogging the EU and the European countries to get their act together, or they'll be left behind. But there's now a dozen of them who have started real deployment. We don't make devices at Ericsson, but we keep track to make sure that there are devices that correspond to the infrastructure that we build. So there's now, as of I believe June, there's a dozen phones and CPEs, which are the thing you use for fixed wireless and so on. So it's happening. And a little glimpse of how this mobile monster moves. You will notice that until a couple of years ago, the world was still running on GSM. This is a network is a live thing. It's not like you just throw away the old network, you put in the new network. So things kind of evolve. But now the top little triangle there is 5G, and it will happen very quickly. It will expand very quickly. And finally, a few topics of what will start standardizing in a few weeks. I think they have one more meeting this year to kind of decide, but those are roughly the things they're looking at. One thing to notice is the so-called non-terrestrial networks, which are essentially satellites, in addition to drones and balloons and whatnot. But the satellite industry has very aggressively moved into the mobile industry technology territory because they figured out that we have the volume and the global scale, and they want in. So now the satellite industry is playing in the mobile standards, and with unknown results, but it's kind of interesting. So, and I will stop here, I think.